from chapter of non-permanent joint. The topic of this example is about the power screw. Okay, here we have a screw thread power. We have a square thread power screw with major diameter of 32 millimeter and pitch of 4 mm, 4 millimeter, with double thread, and it is to be used in an application similar to the figure that we had for transmitting rotational motion to linear motion. Uh, the coefficient of friction between thread and nut is 0.08. Also, it is equal to the friction between collar and the nut. The mean diameter of the collar is 40 millimeter, and the load that need to be transmitted is 6.4 kilonewton. Okay, first at part A, we need to find some parameters of the thread. Some geometrical parameters of the thread, including thread depth, thread width, pitch diameter, minor diameter, and lead. Okay, so let me refer to our lecture note what we had on geometry of the square power screw. The major diameter shown by D and the minor diameter is dr. On this particular geometry, the width of the thread is equal to the gap, which is half of the pitch. Okay, so by using this criteria, we can find others parameter. Also, you have to notice that the depth of each thread is again half of the pitch. Okay, so the mean the mean diameter that we show by dm is a diameter between major diameter and minor diameter. That means it will be located at here. Okay, so that means the mean diameter is somewhere here. Okay, so when we want to find this diameter, if we deduct half of the pitch from the major diameter, we can find this uh, mean diameter, because from the top or from the major diameter to mean diameter is a quarter of the pitch, and in another side here at another side of the thread at the opposite side also we have another quarter of pitch. So this quarter plus this quarter will be half of the pitch, right? So if we deduct this half of the pitch from the major diameter, we can find mean diameter. Okay, so pitch was 4 mm, divided by 2 is 2 minus 32. 30 millimeter is mean diameter of S power screw. Actually, we need this mean diameter for all for further calculations, such as to find raising torque or lowering torque. Always we have to use this mean diameter. Okay, so to find minor diameter is very easy. We just need to deduct uh, pi, the value of the value of the pitch from the major diameters, which is equal to which equals to 28 millimeter. Another thing that we have to notice at the problem statement, it mentioned that this is a double thread, or in another words, we can say is two-way thread. Okay, double thread or two-way thread. That means the lead is 2n and refers to number of ways or number of threads. So 2 times p. That means if you rotate this thread or this screw one complete turns, the knot will move linear 8 millimeter. Okay, in part B, we are required to find the torque to raise and lower the load. Okay, to find the torque that required to raise and lower the load, we can use these two equation 8.1 and 8.2. R stands for raising and L stands for lowering the load. Okay, so in this equation, F is the load that need to be transmitted, or if you want to lift up a weight, is the weight that you need to lift up. dm is the mean diameter that we just found, and L is the lead. F is the friction between coefficient of friction between thread and nut, and again we have same parameters in equation 8.2. Okay, so as mentioned, the load is 6.4 kilonewton, right? And dm was 30 millimeter. So either you can convert this load to newton, then you have to convert all these parameters to meter. I mean, dm or L, you should convert it to meter. Then at the end you will get torque based on newton meter, or you can keep load as kiloton newton, and then it doesn't need to convert others parameters to meter. You can keep them as or you can retain them as millimeter unit. Okay, so when we substitute F dm that we found earlier, L 8 millimeter, so this term here, this term is the torque that we need to raise the load, and here, this is the torque that we need to overcome the friction between collar and the nut. Okay, in this equation, that means you have to use the equation 8. Let me see. You have to use equation 8, 6. Okay, in this equation, Fc, as I said earlier, is the coefficient of friction between collar and nut, and dc is the mean diameter of the collar, which is 40 millimeter. So the summation of these two torque is the total torque that we need to raise the load. Okay, so total in total we need 26.18 newton meter to raise the load. Again, when you want to calculate the lowering torque or lower torque, that means the torque that we need to lower down the lift or the load. Again, we have to add this collar friction or collar torque, because again, at the lowering, at the load lowering, the friction between collar and nut exists, and we cannot ignore this friction. Okay, so one more time we will substitute these parameters for lowering equation, and then we will add to the collar torque. So as you can see here, the lowering torque become negative, right? And that means it doesn't have the self-locking characteristic, but because of this collar torque, the total torque become positive, and we can say that the system in general, the mechanism in general has self-locking characteristic. But if we didn't have the collar friction, so it doesn't have the self-locking characteristic. In part in part C, we have to find the
during
efficiency.
lifting the load.
Okay. The equation for finding the efficiency is the torque that we need to raise the load without friction. That means in the case that coefficient of friction between the thread and knot is 0, we have maximum efficiency or with 100%. So to find the system efficiency, we have to divide this maximum efficiency by, or maximum, the torque of the maximum efficiency by the torque that we need to raise the load. We call that by TO or over TR. Okay, so we have to use this equation 8(4). Okay, in here we will substitute again F based on kilonewton and others parameters based on uh, L based on millimeter, and TR that we found in Newton meter 26.18. Okay, so uh, was Newton meter, right? So these two will get us again Newton meter. These two will generate will product the product of these two is Newton meter, and here also is Newton meter. So the unit of up and down is same. Then we will get the efficiency equal to about 31%. The efficiency of this power screw is 31%. Okay, so next we need to find the body stresses, torsional and compress. That means we need to find the torsional stress on the body of the screw and also compressive stress. Okay, so let's refer to the lecture note. Here we have a series of equations to find uh, different type of stresses on the body and thread of the screw. But among this equation on these stresses, three of them is more important, which are that will be located at the root of the they will be located at the root of the screw. Okay, so basically we have to find these three type of stress. I will introduce them one by one. These three. One of them is the torsional shear stress at the body. Okay, the equation of the torsional. Okay, let me find it. Bending stress, bearing stress. Uh, okay, so to find the torsional shear stress at the body, we can use this equation 8(7). And as you know, in a cylindrical part, the maximum torsional shear stress always located at the circumference of the cylinder. So that means if I refer to okay, let me refer to this figure that I had here. Okay, here the maximum torsional shear stress on the body always is at this outer surface. Okay, the maximum is at this outer surface, which outer surface will be located at the root of the thread, because this is one thread. Okay, this is one of the thread, a square thread. That outer surface of the body is at the same location with the root of the thread. And then we will use this equation to find torsional shear. uh, okay, the next is the compressive stress on the body, which is in y direction because load or weight on the power is in the y direction, and therefore the compressive stress on the body is in y direction. That's why here we show them by sigma y. If we consider that the stress on the body is the distribution of the compressive stress on the body is uniform, that means from here to outer surface, the compressive stress equation, the compressive stress distribution uniform. That means the stress at the center and outer is equal or same. Again, again we have this compressive stress at the outer location of the body, or at the root of the thread. And the other, okay, so we have to use this equation, right, to find the compressive stress on the body or root of the thread. And the other important stress at the root of the thread. This time we are talking about the root of the thread. These two exist on the body, but the location of maximum stress of the body is also fall on the root of the thread. But in this particular case, I mean this equation, I'm talking about this equation, which is bending on the thread, okay, bending of the thread, okay, the bending on this thread, you can find by using this equation. And because the thread is going to bend in this way, right, the uh, by applying the load, the thread tends to bend in this way. So as you can see, the direction is sigma x, in x direction, right? So three stress, one bending stress, one compressive stress, and another one shear stress on the location of the root of a thread. So first we have to find these three main threads at this critical location. So maybe we have some other threads at the center of the thread, right? That you can find in your lecture note. We have some other threads at the center of the thread or at the tip. It doesn't matter uh, because the critical location on the body of the critical location on a power screw is always at the root. And among the thread which they are engaged with the knot, always the first thread is carrying the maximum load. Because if you refer to your lecture note, you can find this statement that the first thread which engage with knot carries 38% of the load. The second thread carries 25%. Third carries 18%. Definitely the fourth one is less than 18. The fifth is less than fourth. Where that the seventh thread can does not carry any load, or is free of load. So by using this statement, we can conclude that the most critical location is the first is at the root of the first thread. The most critical location is at the first thread of is
Find
at the
the
root of the
torsional
first.
shear stress on the body of the screw.
To find this maximum torsional shear stress, we have to use maximum torque, the torque that we use to raise the load. Because when you compare the torque of the raising load and lowering, you can see that we need maximum for raising. It's very logical, right? So I have to substitute this torque into equation, and also I have to substitute dr. Why? Because we are going to find at the body of the screw, and therefore you have to use minor diameter, not mean diameter, not major diameter. You have to use mean diameter because we want to find on the body. The issue is that I suggest you to avoid any confusion of the unit. Better to use Newton meter and then use use meter for dr. Then at the end you will find the result based on Pascal. I believe that it would be less confusing. Next, we have to find the compressive stress again on the body. Instead of F, we will substitute 6.4 kilonewton that was given in the problem statement. Again, here we have to substitute the minor diameter because we are going to find the compressive on the body of the screw. Now, next I want to find the bending stress at the root of the thread, the first thread, because as I told you, the first thread is most critical location. At the root of first thread, again diameter is minor diameter dr, and let me refer to the equation that we had. Okay, nt. The parameters of nt is the number of thread engaged with knot. In this case, because we want to find for the first thread only, that's why we substitute 1 here. But you have to remember that because we want to find only for the first thread, and due to the statement I just mentioned, the first thread will take 38% of the load, so you have to multiply 38% to the load. Okay, you want to find only at the first thread, so you have to multiply 38% of, you have to consider the 38% of the load. So we use this 30% of the load, right? You see, this 38% is not included into the equation. We don't have such thing here, right? Either we have to substitute the number of knots which they are engaging, but I believe that the most accurate method is to only find for the first thread, and instead of F we substitute 38% of the load. Okay, so we will find that the bending stress at the first thread or at the root of the first thread is 81.5 megapascal. Now we have these three stress, which they are in two different planes. Two of them are in the plane of xy, as you can see. This is the plane of xy, and the torsional shear stress is at the plane of xz. So because we have three three stress in two different planes, we have to translate these three into one stress, because we cannot judge based on these three. We don't know that whether this thread is going to fail or no by using these three. So when we want to translate it only into one stress, we can use the distortion energy theory that you had in chapter 3. By using distortion energy theory, we can convert these three into only one Mises stress or effective stress, sigma prime, by using this equation. This equation is for a case that the state of stress is three-dimensional. Okay. So when we substitute into that equation, we substitute these three, add some other parameters or some other stresses are zero, like tau xy, sigma z, and tau zx. These three are zero and these three are non-zero. So you will get that one Mises stress of the this state of stress is 48.7 megapascal. And then we would say that this one Mises stress of the power screw shouldn't exceed from the yield strength of the power screw material. If this value exceeds from the yielding strength of the power screw material, then definitely there would be a bending at the or deformation. It would be we will see the deformation at the root of the thread, at the first root of the thread, and which is not desirable. Okay, in the next part we are required to, okay, I think it's over because we already find the one Mises stress at the root of the thread. Yeah, yeah, this is the end of the problem, and that's it. So if you want to find the safety factor of the power screw, maybe you can use this method. And actually, this is static loading. We are talking about static load. We are not talking about the screw under dynamic load. That has another story, which is not in your subject syllabus. But for this static load, if you want to find the safety factor, you can use this equation. That means Sy over sigma prime. You can find safety factor of the power. Okay, thank you very much for your attention.